All right, good afternoon. I wanted to thank the Council for the opportunity to talk about Panasas. I'm afraid it's a shameful product to promote today, but we're some interesting technology which I hope you'll enjoy. I was particularly interested in a couple of the talks earlier. Joshua made a very interesting point about having a very good sort of benchmark figure and how that applies to real-world applications. With Panasas, we're constantly talking about balance within the whole environment of HPC. Normally the compute nodes get a lot of focus, and then the network and then the storage is an afterthought. If you can't keep the data flowing into your processors, then you're not as efficient as you might be getting the best value for money. So who is Panasas and what do we do? Panasas is a high-performance parallel storage company. We were founded in the late 90s by Dr. Garth Gibson. He's important to us. He was one of the three people credited with writing the RAID papers in the late 80s. He's continued his career with innovation in storage, and he's a professor at Carnegie Mellon University and highly innovative. Panasas delivers a fully supported turnkey hardware, software appliance designed to serve storage to suit the Linux compute cluster market. We have a highly scalable, high-performance parallel file system. We're based on the object storage architecture, and that's kind of the special sauce. We share some similarities with Lustre, which is the other object-based file system. Lustre being an open-source software package, Panasas is a turnkey solution. Both grew from a project that Garth started on behalf of the national labs in the States. And when Garth started Panasas as a commercial venture, he moved away from that project due to some rather stringent ties. Panasas has grown up alongside some other mature storage systems, so we were able to look at how those were managed and ensure that our system was as easy, if not easier, to support and manage as it scales. So why is Panasas here? Well, it's the evolution of storage to support computing. Initially, we have the direct attached storage, which is great. If you have a single machine, you don't want to share that data. But as you want to share it, we turn that set up into an NFS server and use the network file system to push data out. And again, if you've got a single file server or just a couple, then that's easy to manage, and performance is not necessarily an issue, then that could work well. But in HPC, that's often a bottleneck and a management headache with islands of storage. So that morphed into clustered NFS, where you can have multiple filers serving data, broadening that performance capability that still has bottlenecks in the data path. You've got bottleneck here as a single server has to retrieve data and lay it out as you write it, so that for your clients. You've still got those bottlenecks because you've added some extra bandwidth capability. But down here, each server is looking after its own drives. So if you happen to hit this server for your mouse, you want data here, you've got full forwarding, etc. There's been further advances where certain solutions have a parallel or unified storage solution on the back end, so you can eliminate some of those hops, but ultimately performance and scalability is somewhat hampered. With the parallel file system approach and Panasas solutions, we take the metadata service out of the data path, provide you with a map and allow your service to go directly to storage, improve performance and allow a scalable solution to grow. We sell into multiple verticals, pretty much anyone who has a need for high-performance computing with Linux clusters and large data requirements. We also have a similar splash page, which is a bit unlike the one shown earlier for the HPC Council. Just a selection of some of our customers. We have a lot of very well-known customers using the Panasas file system, and a lot of them are happy to talk and give customer references. So a quick look at the hardware that Panasas delivers. We have a very modular design, allowing you to start with a small solution and scale as your needs grow. We scale virtually linearly for capacity and performance. It's a blade architecture designed to deliver data and not processing cycles. There are two different types of blade in our system, the director blades and the storage blades. All data and metadata is kept on the storage blades. We don't store anything on the direct blade itself. This is purely a metadata manager. It's a RAID reconstruction engine. It's a manager for the system. We're building a cluster, so we manage that ourselves. and it's our gateway devices for other for NFS and CIFS gateway CIFS protocols as opposed to our parallel protocol which goes direct to storage. Each chassis has integrated Ethernet switches, 10 gigabit Ethernet connections to the outside world. We have InfiniBand gateway devices to connect into InfiniBand networks. We have multiple switches for resilience and extra performance per shelf, as well as power supplies and a battery backup. So we have a battery in each shelf which allows to protect cache data in the event of power outage. The object storage architecture, this is really key to how we can do things very differently to traditional storage solutions, giving us the benefits of scale. We take the data within a file and attributes associated with it, timestamps, ownerships, permissions, etc. We can encapsulate those together to create a virtual object. But we can also inject attributes at this level. This allows us to do RAID on a per file basis. So every file has its own RAID layout. This eliminates the need to set up LUNs in the storage layer, in the hardware layer. So there's no LUNs to set up, we can just bolt the systems in, they come pre-formatted from the factory, and just add them together to scale. Once you have this virtual object, we break it up into smaller component objects and send each of these to a different storage device in the system. And we use 64K chunks by default, still a relatively large amount of data in storage terms, as opposed to blocks. Once this is sent to the storage blade, we can forget about it at the high level. It's then the job of the storage blade to take that into memory and then do the block allocation. With the typical NAS device, I think there's a study that said 90% of the filer's workload is block allocation. So you get a good distribution of the workload across multiple devices. As this look in practice, we have compute nodes connected by a network. And as long as this can pass IP packets, we can talk to it. We've separated out the director blades, which are our metadata managers, from the storage blades for clarity, but they will live in the same chassis or multiple chassis. The compute node will have small communication with the director blade, asking where is the data I'm interested in. The director blade will query the storage to get a layout. We'll return this layout as a map, and also authenticate the request with your capability. A bit like a security certificate, you can present to the storage blades to show you have the right credentials to retrieve the data. Once you have the map and the capability, any of the compute nodes can talk to any of the storage devices directly and in parallel to retrieve the data. The more devices you have in your storage array, the faster you can retrieve data. Panasas solution currently is around 1.5 gigabytes per second per shelf for our top performer. And as you add shelves together, that's linear scalability. You can build systems to suit performance requirements or for capacity requirements. We also use the director blades as gateway devices to provide access to the same data concurrently using standard protocols for Windows and for other non-Linux clients. The Panasas solution is extremely simple and easy to manage. We want you to be able to get on with your core business rather than spending time managing and administering a complex parallel file system. Just a quick graphic showing how simple it is to install. We configure a director blade with an IP address, net mask, bring it up on the network. We then ask a handful of simple questions around network connectivity, not around the storage configuration, because we do that on a per file basis within parallel file system. You can see here, it's just a handful of questions that need a non-default answer. The time it takes to answer those is to configure the director blade. The rest of the blade will then obtain configuration information using DHCP on a private port to get an IP address. It's configured within the director blade, and then other configuration parameters using RPC calls. So roughly the time taken to boot, you have a configured shelf. Once it's configured, you can install an RPM on a Linux client, and you have a parallel file system. So we have an UDI, an out-of-box experience. It says installing a shelf of Panasas, having a parallel file system up and running should take less than an hour. Now, we encourage customers to fill this as quickly as possible, and then you can expand the system with online provisioning. So as your needs grow, you just bolt more shelves together. They do the same lookup on the private port, get their configuration information, they will match software versions automatically, and again, in the time taken to boot, you've grown your file system. We have a capacity imbalance at this point, so we will target the new storage, the new creates where possible. But we also have a mechanism for moving component objects around within the system and just update the map of where they live. So this is a process that happens in the background, so it won't impact production performance, and over time capacity is evened out. And this is an ongoing process to continually monitor the file system as you create and delete files. We manage to distribute the data evenly across every device to keep each device running as efficiently as possible. Because we do RAID on a per file basis as we create the data, the volumes within the Panasas are a virtual volume. Each volume is free to use all of the hardware devices in the array. It's a mechanism for us to break up the metadata workload. Each volume is assigned to a different direct blade in the system to give us a scalable metadata solution. We have a single namespace. So from a single mount point, you can access all of the volumes within the Panasas solution, and also from multiple Panasas installations. If you decide to configure multiple shelves as different installations, each their own management domain, you can access the volumes on multiple systems from a single mount point if you choose. You also have the option for additional mounts to mount point as normal systems. Panasas is a highly resilient, reliable solution. You just plug it in and just get on with your daily work. You don't have to manage data loss and the likes. So we have a lot of fault tolerance within the system. We cluster director blades together as the managers of the array, because they have fault tolerance in that service. We have the metadata managers. We don't store any data on the director blades, but we do maintain transaction logs in memory. It's a journal file system. And we can mirror those journals, those logs between director blades for automatic failover of the metadata service. We're constantly checking the drives within the system. So we're probing the media on a cyclical basis, looking for media defects and errors within the system that we repaired in the background. And we monitor the trends and behavior of the drives. If we see a disk is having trouble with unrecoverable read errors or bad blocks, we can predict a failure. And provided the drive doesn't fail instantly, you have the option to drain that blade. So we just have an extension of the component migration to move data away from that device, allow you to replace that blade without a reconstruction event. When we look at RAID, we'll see that even if that device fails part of the way through the drain, it's a saving because we only repair the data on that device when it fails, not the entire drive of the block. In the hardware, there's no single point of failure. We have redundant power supplies, we have a battery backup module, which is there to protect the cache data, but it has an added benefit that allows us to gracefully shut down the drives in the event of power failure. So we're never allowing the heads to slam into the disks, preserving the resilience of the drives themselves. A lot of customers who've suffered double drive failures with other systems will tell you it's most likely after a power outage. So the RAID features, how we do RAID on a per file basis and how we can use it to improve efficiency. Small files and directories are RAID 1, so we'll just have a mirror between two storage blades within the system. As a file grows beyond 64K by default, that's our definition of a small file in the system, we transition from RAID 1 to RAID 5, adding more storage blades into the stride. Now, because we want you to be able to use all of the devices in a system, and we want you to have large systems, traditional RAID doesn't do that very efficiently. An example I have is 10 shelves of Panasas, lots of customers with 10 shelves or more. You would need a stride width of 100, have 100 storage devices. Traditional RAID would require a stride width of 100 to hit all of those in a single system. That's very inefficient. You will quite often have to have partial stripe updates where you're required to read some data before you can calculate the parity and write that out. But also, if you've got a client reading from 100 devices on a network, a gigabit connected, a client with either an InfiniBand or a gigabit or a 10 gigabit connection will be overwhelmed with 100 streams from gigabit connected clients. We've introduced a two-level heat-clustered RAID layout that maintains a sensible strike width of approximately 10 devices, and we will write data to those 10 until we hit what we call a strike depth. And that's approximately 2,000 strikes by default, about a gigabyte of data. If your file is still growing, we'll pick another 10 devices from our 100, however many we have, and continue to grow the data there This is building multiple parity groups into a single file. It also allows us to distribute the data efficiently from multiple clients writing multiple files across all of the devices in the system. For the reconstruction, because we're calculating parity with the client as it's generating data, we have a RAID engine that's always in sync with the size of your cluster to write the data. For reconstruction, we use our director blades as the RAID reconstruction engine. We cluster them together to provide a compute engine. We do an object reconstruction, so we're not doing a block level reconstruction. We have distributed spare space in the system. So when you're calculating the reconstructed data, we don't have a single device that's the target becoming a bottleneck. We can read and write in parallel to all the surviving devices in the system. This gives us a scalable reconstruction performance. The bigger your system is, the faster you can repair a failed device. So we maintain a very steady reliability, whether it's a single shelf or 10 shelves or more, of recovering data. And so a couple of slides from an IBM presentation which looks at clustered RAID. So this is the way forward if you want to build larger systems to distribute data and workloads more evenly. On the left we have traditional RAID, where you have the LUNs, the volume types are just a handful of the drives in the system. And the declustered RAID, where every device is taking part in all workloads. And then for reconstruction, you can see where the bottlenecks come from, and how we can eliminate that with the declustered RAID and distributed spare space. Panasas has tiers of parity within the solution to help protect data. We have parity as we strike data across multiple devices, and parity within the device itself. So this is providing parity across sectors of a disk. So if we have an unrecoverable read error within the drive, as drives are getting larger, they're getting no more reliable, so the probabilities of unrecoverable read errors are getting higher. So during a reconstruction event, you need all of your surviving data to be correct. You can protect the unrecoverable read error potential using parity at the drive level itself. So that's sort of the technology behind our products. We have a product family, ACTIVESTOR 11 and ACTIVESTOR 12 currently, and we're launching an ACTIVESTOR 14 product next week, so I'll give you a sneak preview. Effectively, our product family meets different performance, capacity requirements, and different budgets. ACTIVESTOR 11 and 12 separated by either a single 10 gigabit uplink or dual uplink primarily, so giving you about a gigabyte per second of maximum throughput on an ACTIVESTOR 11 and 1.5 on the 12. There are some other subtle differences, changes in cache size, etc. that will give you added benefit with the ACTIVESTOR 12. And then the soon-to-be announced and launched ACTIVESTOR 14. This is the integration of an SSD device into the storage blades themselves to help increase the performance of small file and random access workloads. Again, we do very well with our current technology because of the RAID layouts. Small files are mirrored for additional performance. The overhead is not great in the capacity and the scheme of things. The other thing, by coupling these devices together cleverly, we get a very efficient use of our spindles. We're about twice as fast per spindle as the competition. And we continue to be very easy to use and deploy. There's no application layer changes required to make sensible use of the SSD technology. It's still the same looking hardware from the outside, still the same field of placeable units. And looking inside the blade, you can see we've got the SATA drives on the SSD sitting up here. We use the SATA drive to store in-blade metadata. So we've effectively got a virtual file system that strikes data across multiple devices, and then a real file system doing block allocation within each blade. We keep that block allocation on the SSD, and we also keep files of 60K or less on the SSD. This is a huge increase in the IOPS performance, and also a little increase in the streaming bandwidth as you get a lookup the data that lives on the SATA drive and get that lookup on the SSD. The lookup also helps us with reconstruction. We do an object reconstruction, so we have to go and find the objects that need to be repaired, and we can find that information more quickly from the SSD. And we also changed our vertical parity ratios, so we get a much higher density improvements. So we've gone from 11% overhead to 3% overhead. We also saw 12K with every inode effectively, so we much faster than very small files. We did a study of large and small files, and the majority of HPC, although they will tell you their workloads are large files, have a very high percentage of small files in the mix as well. Hurrying up because I know I'm running out of time. And this was a more detailed look at the performance of each spindle. You can see here that we're sort of comparing ourselves with high performance SAS drives, 15K and 7.5K SATA drives from the ACTIVESTOR, and also 10K SAS drives. We're very much at this level of performance. I've taken out the dollars per gigabyte per second metric. I'm allowed to share that until it's launched. But we're about sort of half or a third of the cost of competition at that point. And in summary, why Panasas? Leading in performance and scalability, ease of use and ease of manageability to allow you to get on with the type of workloads that the business focuses on. I think that's it. Any questions?